Hey everybody, today we're going to start a new unit and it's going to be about surface area and volume. And it really is just a progression from our area unit. You know, we talked about the area of a two-dimensional figure. We talked about a whole bunch of them, everything from a regular polygon to a circle or whatever. It ends up being a really good segue to 3D figures. Because essentially, if you're dealing with a 3D figure, it really is just a bunch of 2D things put together. Now, the most common thing we're going to deal with is a 3D object with faces that are all polygons. That would be something like that right there. It's a 3D object. Technically, that is a rectangular prism, but you don't need to know that right this second. It's a 3D object made of polygons. So all the faces are polygons. If that happens, it is called a polyhedron. All right, now, just to get a little bit of vocab for you, just to make sure you know what's going on. If you have two faces of a figure, they meet at an edge. And if three edges intersect, it creates a vertex. So I want to throw that in here, and I'm going to kind of demonstrate. Again, we're going to look at your rectangular prism so I can demonstrate here. So essentially, let's say you had this top piece right here, and then this piece to the side right there. Where the two faces meet would be considered an edge. Now, if you were to look at a third part now you're talking about a third face. Let's look at that one. The little corner where all three of those end up meeting, that would be a vertex. Now, part of why this is significant is because we have a formula. It's called Euler's formula. Now, a lot of people get it wrong. They say Euler. I guess in other languages, sometimes it can translate that way, but generally speaking, we call it Euler. He was a mathematician way ahead of his time. The farther ahead you get in math, the more you will learn about this dude. As it is right now, all we need to know for the sake of what we're dealing with is Euler's formula. It is my fave. Okay, it's not really my fave, but you'll see where I'm going with this here in just a minute. Now, what I want you to do, I want you to draw, let's do a square pyramid. Now, if your artistic ability is not great, then you could really just draw a rectangle. And I think there are better ways of drawing this, but I'm just going to give you one. You could just draw a rectangle and then make a point up above, giving it a little bit of perspective here. There you go. If you make a point above the rectangle and then you connect all four corners to the top, you create what looks like a pyramid here. Now, that is not perfect. There are all sorts of ways you could draw one of those, but hopefully you can kind of see what's going on here in that we have a base, and then we have four triangular panels that all fold up to get to the top. This is an example of a polyhedron. It has polygon faces. It actually has 5 faces. We know that it has 5 faces because it has the bottom, and then it has the 4 triangles that go around it. Now, Euler's formula is going to come in here in just a second, and you're going to see why. The number of edges on this figure, so that would be anything that connects 2 polygon faces. So that would be an edge. That would be an edge. 1, 2, 3, 4. And then you also count the bottom because there are 4 edges on the bottom as well. So what you have found here is this thing has 8 edges. Now, if you look at the vertices, a vertex is anywhere that 3 faces come together. Now that would be right here. Let's make these a different color. That would be a vertex. So you're essentially looking for the corners. 2, 3, 4, and then 1 at the top. Now that actually has all 4 of those edges up there coming together, but 3 or more essentially. The number of vertices, we were able to count 5. Now, Euler's formula relates this, and it always holds true for a polyhedron. The number of faces plus the number of vertices equals the number of edges plus 2. And that works every single time. We could even test it with the example that we just did. Faces, 5. Vertices, 5. Edges, 8. Is 5 plus 5 equal to 8 plus 2? Absolutely. It checks out every time. So there's a lot of value there. It's a great way to check your work. If you think you know how many vertices something has or how many edges, putting it in there and trying to figure it out to verify makes great sense. All right, we're just going to go through some practice problems, and we're going to apply that, and we're also going to talk about surface area toward the end. We're going to introduce that idea, and we're going to see where we get. So first of all, just basic idea. Is something a polyhedron, yes or no? In this case, the answer for number 1 is no, and the answer is pretty simple. Circles aren't polygons. You know, you're looking for how many sides a polygon has. Well, a circle doesn't really have sides. It doesn't really work that way, so you can't really call it that. So if a circle is not a polygon, that means a cylinder is not a polyhedron. Now, that being said, you could still find the surface area of it. We will get to that later. All right, number 2. Well, we got a whole bunch of rectangles. So you've got all these different polygons, which these are essentially rectangles. And the rectangles come together, and they formed a rectangular prism. All right, last but not least, it said explain your reasoning. If it seems like I'm rambling on here, I'm just trying to explain where I'm coming from. The third one also checks out. Now, if you look closely, you'll notice it's 3 rectangles, but it's also 2 triangles. So they are all polygon faces. If you're wondering, this would be a triangular prism. And that also counts as a polyhedron. All right. As we go through the next 3, we just want to work on our faces, vertices, and edges so that we can make sure that the formula works out. So number 4, faces. It looks to me like I've got a couple of trapezoids, and then I also have a few rectangles that have to wrap around. Vertices, those are going to be the corners. So 1, 2, 3, 4, and then you've got 4 more on the bottom. So that means we have 8 vertices. Now edges, this is where it's going to be a little bit tough. We've got a whole bunch of them because we're going 1, 2, 3, 4 across the top. Then we're also going to go 1, 2, 3, 4 down the sides. And then for good measure, we also have 1, 2, 3, 4 on bottom. So the edges were actually 12. Now let's double check our work with Euler's formula. Faces plus vertices equals edges plus 2. 6 plus 8 equals 12 plus 2. That is a check. It totally worked. All right. Let's try it with number 5. Now, this is a pentagonal prism. That's kind of a weird one, but we'll just go with it. The faces, I have 2 pentagons, and then I have 5 little panels going around it. That is 7 faces. Vertices, if you look, you've got 5 in the front, you've got 5 in the back. So you've got 10 vertices, 5 in the front, 5 in the back. Edges, I drew out the last one. I'm not really sure I'm in the mood to draw this one out, but you essentially have 5 in front, 1, 2, 3, 4, 5. You have 5 in back, 1, 2, 3, 4, 5. And then you have 5 connecting, 1, 2, 3, 4, 5. So the edges are going to be 15. Again, Euler's formula is very valuable for a double check. So 7 plus 10 equals 15 plus 2. And you're just sort of glancing at it to give yourself a little yes or no. Does that check out? Does it not check out? 7 plus 10 is 17. 15 plus 2 is 17. It checks out. All right, number 6, the last one in this category, we've got a triangular prism. Triangle in front, triangle in back, and some rectangles connecting them all together on the side. Faces, we've got 5. Front, back, and then 3 around. Vertices, you've got 3 in the front, 3 in the back. Edges, you've got 3 in the front, 3 in the back, and 3 that are connecting. So again, same idea as 4 and 5. We just sort of want to go through and double check when we are done. 5 faces, 6 vertices. 5 plus 6 is 11. 9 plus 2 is 11. It's always plus 2. It checks out. We are good. The last thing I need to address with you, and this one may take a second here, I'm actually going to pull back and show you the formula sheet. It's not really a sheet. It's actually what you get when you click on the formula button on the end of course exam. Even if you are not in this state, you will still probably get something very similar to this. It gives you conversions, gives you some trigonometry, which we will do later, and then it gives you some areas. Now, what's annoying is it doesn't give you like the area of a trapezoid, which is something that people forget all the time. It gives you the ones that you already know. And then it gives you volume. What you should notice is that it did not give you surface area. So when you are told to figure out the surface area of a figure, you are going to be expected to go face by face, piece by piece, and then add up what you get. And so this is where you have to get a little bit creative. Okay, there are formulas for some of these, but the basic expectation is that you can figure it out without a formula because they're not going to give it to you and you might forget. So here's what we're going to do. We're going to try to piece it together bit by bit. We've got ourselves a 5 by 9. We got a 5 by 9 rectangle. It didn't highlight very well, so I'm going to have to wing it here. Not a big deal. We've got a 5 by 9 rectangle, which would then have a surface of 45. And it is going to be inches squared, by the way. So if you're thinking about the last chapter and you're like, well, you didn't label it, just work with me. We'll label it at the end. Then you've got a 12 by 5. That's over here. And that's going to be 60. Now, if you were to look at the rectangle all the way in the back, and now it's kind of getting tough to see because we've got a lot of drawing going on here. That's a 5 by 15, so that's 75. Now, the top and the bottom are the same, so as soon as I get that number, I can just multiply it by 2. Now, I want you to ignore the 15 for a second because the right angle is right here. So if I'm going to figure out the area of the triangle on top and the triangle on bottom, what I'm going to do is I'm going to treat the 12 as the base and the 9 as the height. Ignore the 15 because it's not really going to help us. Now, if you did 9 by 12, you'd get the exact same answer. 9 times 12, 12 times 9, either way, it's 108. But since it is a triangle, and remember the area of a triangle is, and that's not going to come out very well because it is in yellow, but that's okay. The area of a triangle is 1/2 base times height. So if I'm going to put in a 9 and a 12, I'm going to get 108, but I've got to do half of that, which would be 54. Now, I have a 54 on top. The bottom is the same as the top, so I'm going to do another 54. And then from there, if you want to know the surface area of a polyhedron, you just add the 4 numbers up. Now, I know how to add, you know how to add, everybody knows how to add, so I think it's time that we just move on with our life and we call it 288 square inches. Okay, so you take every face and you add up every single area you can come up with. All right, for the next one, this one's a little bit tricky. Let's start with the pentagon. Now, the area of a pentagon is 1/2 apothem times perimeter. So that's going to be 1/2 times 4.1 times the perimeter would be 30, because we have 5 sides and each side is 6. Ignore that 15 for a while. We're going to take care of that here in just a second. So you get out, it doesn't really matter what calculator, but you might end up needing one for this. You end up getting 61.5 centimeters squared. Now, we will need 2 of those because we had a pentagon on the left, we had a pentagon on the right. Now, as far as the rectangles are concerned, those are just going to be base times height. Those are going to be 15 times 6, and that would be 90 centimeters squared. Now, here's the catch. There are 5 of those. So when it's all said and done, you're going to take the pentagon area and multiply it by 2, and then you're going to take the rectangular area and multiply it by 5. So you end up getting 123 plus 450, which would be 573 centimeters squared. So you have to take every single last face that you can come up with and figure it out. All right, now the last example of the day. It is by far the most commonly missed problem that we do as far as surface area is concerned, at least in the early going. And the reason is we have to think back to the very beginning of the class. The very first lesson that we ever do in this class, well, that I do it based on my order, we talk about nets. We talk about how you can make a 2-dimensional figure from a 3-dimensional object if you just flatten it out. Nets are actually a great way to approach surface area, because if you draw the net out, then you can see every single surface in action. The reason I bring that up is because when you're dealing with a cylinder, it is very hard to visualize what is going on in a 3-dimensional manner. So I want you to think of it as a can of soup. If you were to take the top face and then the bottom face, and then try to figure out what the surface area of the soup label would be, if you roll a label off of a can of soup, and you can do this with a little 20-ounce soda, sometimes the label comes off, or whatever you do, maybe when you get bored, that's something you do, it makes a rectangle. If you were to peel that label off, it actually makes a rectangle. So really, when we're talking about surface area, we have a top circle, and the area of that is just going to be pi r squared. So 3 squared is 9. So you get 9 pi. And then you get another 9 pi. So really, the only tricky part is, how do we figure out how long the label is going to be? That's really the only question that comes into play here. And how you do it is you have to think about the point of the label. The label exists so that it can go around the circle. So whatever the circumference of the circle is, that's what the label is going to need to be. So in this case, look at your circle. If the radius is 3, the diameter is 6, which means the circumference is 6 pi. Which means the area of the rectangle is 6 times 6, which is 36 pi. So if you want to know the surface area of the entire cylinder, you would do 9 pi plus 9 pi plus the rectangle, which is 36 pi, which would add up to give you 54 pi centimeters squared. Now, in this case, if you want to leave it in terms of pi, that would be totally fine. If you wanted to get out a calculator and you actually wanted to do 54 times pi and then round it off, you could get 169.65. And that could also be centimeters squared. Both answers are perfectly legit. It doesn't really matter which one you use. But again, the biggest key is understanding how in the world you can figure out the surface area, and you have to base it on the length of the label, and the length of the label is the circumference of the circle. That's going to be the toughest one. It's going to take a lot of getting used to. So if you don't pick it up right away, it's not a big deal. We're going to keep practicing as much as we can. All right, I hope this helps you out, helps you get started. I will see you next time.